Our speaker today is Tomas Petricek. I've known Tomas for quite a long time, since he was a PhD student. I'm a big fan of his work. He works at this in this kind of difficult spot where you try to interact really profound theory with very interesting applications, practical application. And he does nice theory, but he's also quite an impressive hacker. His PhD thesis was on context-aware computation using type systems to track resources and capabilities in programs at the University of Cambridge with Alan Mycroft. He worked quite a lot with Microsoft Research on developing F# tool and improving the F# ecosystem. He has a pretty good book, which I would venture to say is one of the standard textbooks on F# and data science. This data science angle he pursued while being also associated with the Alan Turing Institute for a few years. And he worked a lot on this kind of interaction between programming languages, data science, not just programming language in the sense of the theory of the programming language, but also the wider ecosystem, having nice tools and nice environments for doing programs motivated by data science. I think we can learn a lot from his ideas. So, Tomas.
Thank you. Yeah, I think that pretty much sort of covers, provides a perfect introduction for the talk, because the data science aspect is what I'm going to talk about. And I think in a way this is sort of, I'll give you an overview of 3 different projects that I've worked on, and then reflect a little bit about what's interesting, what's common there. So it's going to be mainly some live demos of things I've actually built, but I'll sort of, after every demo, I'll insert a little bit of theory for those of you who are interested in that space a bit more, or sort of references to why this is theoretically important. So I'm going to share my screen here. All right. And really the sort of motivation, or what is this talk about, is sort of how I got interested in these problems is largely by sort of looking at how new kinds of users want to work with data. So the talk is really sort of inspired by this trend in media of using more data, and in contrast to the current trends in information sharing on the internet, my talk is about making facts great again. So the motivation here is a lot of people are sort of trying to do something with data, like journalists who want to build some nice data visualizations. And right now, this is really, really hard. So it's sort of something that the New York Times can do because they just have a full team doing it. But it's something that's very hard for others. So in other words, what I'm sort of interested in, and what is like a background theme for some of this work, is making simple data exploration accessible to non-experts in various forms. Now, the obvious question these days that you get asked is, will a deep network make my work obsolete? And I obviously think it's not the case. Otherwise, I wouldn't be doing it. I think the reason here really is that sort of machine learning and all the sort of work in that space is really good at solving hard problems. But what you get from the programming languages thinking is more sort of design question of how do we really think about the problem. So a lot of this work isn't about, a lot of what I'll be showing isn't really about sort of solving particular hard problem. although there will be some hard problems solved by machine learning in bits of the talk, but it's much more about sort of how do we think about programming? How do we think about interacting with data? So it's really more about design than sort of specific technical innovations. And I'll start in a way with the sort of oldest, simplest thing I've been involved with. That's a project called THEGAMMA, and it's about simplifying programmatic data exploration. So I'll start, I'll sort of jump ahead into an example I've got here. So you can I'll give you links to everything later on, but I've got a little programming environment here loaded already, and it runs in the browser, and I can start typing code, and it's a little programming environment for exploring data. And all I have to know really is that there's a data source here called World Bank. And this is a reference to the sort of World Bank data set, which collects various indicators about countries. And I can explore this data by typing dot and choosing, as you would in many programming languages that have objects, by choosing one thing from a list. So I can get data by country, and then I can choose whatever country I'm interested in. So let's say I'm interested in the United States, and then I can type dot again, and it offers me a list of categories of data that it has about the United States. I can say climate change, and here I can say I want to look at carbon emissions in kilotons. So now that I've got this, and this is where I actually have to do some coding, although not a lot, I can take my data and pass it to a charting function and get a really sort of quickly a chart of the carbon emissions in the US. Now my data ends in 2010, so I'll need to get a more recent source, but that's the principle. Then I can do the same thing here and just sort of replace a bit of code, type dot again, and let's have a look at China, for example, and I'll add China to my chart. Now I don't have very nice labels, but it's sort of, the blue was the US, orange is now China. And partly the motivation for this is that very often you can sort of get a lot of different perspective on the data, on data. So one interesting thing, and really this is something that I would like non-experts to be able to do, is if you have data visualization like this, maybe you want to change it from carbon emissions in kilotons to carbon emissions in metric tons per capita. So this is sort of how much CO2 generates one person living in the country. And if I make the change, then you'll see the data looks very different. So China is sort of growing fast, but was still here at the bottom, at least in 2010. So the motivation here is really sort of how can we make this kind of simple data exploration where you're just fetching or querying some data really, really easy, but still keeping to the programming environment. The way this system works is that the language here understands the data, which means that when it does things like type checking, it actually sort of takes into account the specific data sources. So the members that you see there when you type dot, they're generated from the actual data or from metadata about the data that we're accessing. And the sort of fun thing here is that you can do all programming or almost all programming just by typing dot and selecting a member. So sort of idea is, can we use this very, very simple interaction to encode a lot of different sort of data access problems? And there is some interesting type theory behind this. And I've been sort of looking into this problem of whether non-experts can use this. And it's really, the sort of work is really motivated by this sort of gap in data tooling, where on one hand you have things like spreadsheets, and everybody can use spreadsheets, and they're great for solving relatively easy tasks. But once you have something that cannot be solved by spreadsheets, you have to sort of learn much more, and you have to sort of learn how to program, and that's quite a sort of gap in the knowledge that you need. So you need to learn much more, and then much fewer people can actually do things with programming, but then you're sort of unrestricted in what you can do. So what I'm trying to do with the Gamma is fill the bit in the middle, where it should let you do more than spreadsheets, maybe not as much as programming, but it should be easier than learning Python, maybe sort of harder than clicking around in Excel. But one thing I've been sort of looking at here is, to what extent can you really make this feel a bit more like Excel? So I've got another data source here where the system handles this in a more clever way and is actually able to give you previews of the data. So this is a data source containing a list of all Olympic medalists. So there's sort of one row for every medal awarded in the Olympics, starting with swimming in 1896. And I can do various things with the data, again, just by typing dot. But rather than sort of navigating to a particular data source, I can now build a query, for example, to filter the data and say, I'm only interested in the Olympic Games in Rio 2016. And then I have only 2016 Rio data. And then I want to do some other aggregations, like group the data. And you can really sort of do all this work just by typing dot and choosing from a list. But there's also some user interface that basically gives you access to the same list, except it's not in the code, but somewhere in the UI. So here I can say, maybe let's group the data by team, and for every team or country. And again, you can sort of see the list here, or if I type the dot here, it will be the same list. I can sum the number of gold medals, and then I can sort the data by who's got the largest number of gold medals, and then I can take the first 10 and get a data series with the team name as the key and the number as a value. And again, this gives me a data I can pass to my charting function. And I can generate, well, this doesn't fit very nicely, I'll make it less. This is a chart showing the top 6 countries by the number of gold medals won in the Olympic Games in Rio. So the basic coding that I had to do here is very much the same as what I was doing before. The only difference really is that previously I was just navigating through a data source. Now the same mechanism, this sort of language with just dot, encodes something that's more like an SQL query. So the sort of interesting technical bit behind this is that people have been trying to do various work on sort of fancy types for tracking things like data frames or structured data. And there's a lot of work on this thing called row types, where a row type is an idea that you have a type that represents something like a record with different labels of different types. So here I have an expression E, which has a type with labels F1 to Fn of types T1 to Tn, just like a table. And you can have operations that sort of do something on the data, like drop a specific column, which will also drop this from the type. And that does happen in my case, where if I say Olympics, drop columns, and I drop the athlete, then this is no longer in the type, and I can no longer drop it again. So, but the way I encode this is I have these generated provided nominal types that are generated behind the scenes, and the drop is just a normal member of the object, which sort of has some nominal type, or the object has some nominal type, the result has some nominal type, and the types are generated behind the scenes to have the right members. So you have sort of extensible type system where the types are generated. And I think this is a sort of technically a nice trick that actually makes this work. So this was one thing that I've been working on, and that really sort of motivated me to look more at this non sort of code oriented approaches. So what I've been doing here was very simple programming, but it still involved some code. And when you look at how you do this work, you really sort of, more than programming by writing some text, you program by interacting with the environment. And you program primarily by this operation of choosing a thing from a list. So the sort of next question I was exploring is, what if we actually represented the programs not as source code, but as a list of interactions with the environment? And still focusing on a sort of data science programs, but without the sort of language being so primary. So I'm going to show you another example here, and this is a little sort of programming environment, again, running in the browser, where the code editor is now replaced with a sort of more visual environment. And the program here is really represented as a sequence of operations. So what I do here, and I predefined a value that represents my input data set, and I can now say load this data set. And then the data set has some rows, and I can access a specific row. Let's see, I'm going to pick a row on the index 2000. I'm going to access that. And so you can sort of see it's, again, just selecting things from a list, except it sort of works for when I'm choosing a member, but it also is working here when I was choosing an argument. So it sort of looks at the environment and figures out what are compatible arguments in scope. Now, one interesting thing you can do in this setting is that right now I was just basically constructing some program without actually running anything. But I've made evaluation an explicit operation in this programming environment. Just like you can write code, you can evaluate bits of code. And this has some interesting effects. So if I select this, then it says it's not evaluated. You can double click to evaluate. And if I see what's available, it's just this lookup operation that finds a member of this row by name. But if I select this loading operation and actually evaluate that, I have to move my Zoom window a bit so that I can click there. Hang on, go away. All right, this is now evaluated. And you see it's just a data table which contains lists of aviation accidents in the EU with data for different registration of the airplane, country where an accident happened, and then for every year there's a number there. And now the interesting thing that's happened is that this, this row at index 2000, I still haven't evaluated that, but I can already access the members because the sort of evaluation enriched the type information I have about the data. So there's sort of interesting operation here where when you evaluate something, the information from that actually are fed into the type system, which then propagates it through the program. And I can do things like access the where a thing has happened. So what did I want to do? I wanted to show you something else. I wanted to show you how to filter the data to only get the data where people have actually been, or count I basically want to count how many people died in aviation accidents. So I want to filter it. I'm looking at the row 2000 where this is some injury, and I can create basically a filtering constraint where I say, is this a row where the victims have been killed? And if I evaluate this, I get false because that's not the case for this row. But what's interesting here is that I can sort of code against this concrete data point, a randomly selected row, and then abstract that into a reusable function. So rather than sort of constructing function by saying function taking an argument x, where I have no idea what x is, I can say pick a sample row, construct a query, construct an expression, and then turn this into a function that takes, and here I can select what's the argument of the function. So it's going to be an individual row. And now I've constructed function, but I did it in a way where I can actually always see concrete values. And what I can do now is I can go back to my data source and say, I want to filter this, and I want to filter this using this function. And if I evaluate things, then I get data just on the accidents where people have been killed. So if you do a bit more work, click around a bit longer, then you can construct a query that takes the sample row, filters some data that is not relevant, looks at the number of people who have been killed, then sums the total number for different years, and then plots this in a chart. So you can, again, do a basic data visualization that does some data filtering just by clicking around in the programming environment. And this is sort of, this still looked very much like code, but the sort of underlying mechanism is quite different, because rather than representing the program as a source code, it's really represented as a list of interactions, which can be things like access a member of an object, invoke some operation, define a new value, evaluate a sub-expression, or take a block of code that you have and sort of turn it into a reusable function. So the sort of representation is different, and it has some interesting problems, like rather than checking text, type checking text, you're now sort of type checking a list of interactions. So it does have sort of interesting different structure behind it. I did show you how sort of adding an evaluation operation can affect the types, because now you have more information that you can propagate through your program. And I did also, yeah, that's what I did show you. But it lets you do some other interesting things, like, and this is something I've been sort of doing before already. Rather than exposing an interaction just through code, you can expose it by some sort of interaction with a visual representation of the data. And another interesting thing is you can actually represent the same list of interactions, the same program, as code, which is what I've been showing, but you can also display that in different way. So just to give you sort of two more quick examples, what I can do here is I have my data source and I evaluate this. Then what I can do is, rather than sort of tediously construct the code to do some operation on it, I can say I want to filter it to just get the rows where victim equals kill. And if I click here in the user interface, in the sort of preview, it will invoke the corresponding interactions, corresponding sort of code operations, and those will just be sort of visible here in my code. So I can do all my filtering. Now I'm not going to do the whole thing here, but you can see how this basically lets you sort of construct a lot of code in a more spreadsheet-like way by interacting directly with the preview. So if I, for example, want to sort the data by 2016, I do this here in the preview, and I'll find that there was an accident where 13 people have been killed in Norway. And you really can do a lot just by interacting with the table, but behind the scenes, what's going on is that you're constructing a program, and you can see the program here as well. So that's sort of one fun thing that this representation lets you do. Another fun thing that this representation lets you do is that you can look at the code in a different way. So what I've got here is, again, the representation, what I'm doing here is exactly the same as before. So I can sort of create my name for a file I want to load, and then I can say, use this data object to load the file, and then I can evaluate this and see my data, or I can do some filtering operation, or maybe sort this by the number of accidents in 2015, and I can evaluate this. But rather than looking at code, I'm now showing a different representation of the same list of interactions, this time in something that looks more like a spreadsheet. And there's much more you could do here. You don't really, I mean, this is just sort of putting the operations into the spreadsheet as individual formulas, but you could actually sort of embed the whole resulting table and have this as part of the spreadsheet. But this is just a sort of early demo of what you could do, and there's I think much more that could be done there. So again, it's this sort of idea that if you represent program as a list of interactions, you're sort of abstracting away from the concrete representation. That can be code, or it can be other interesting things. For example, something that looks more like a spreadsheet. So all of those things that I was showing so far were really more about very simple filtering, very simple querying, things that don't require a lot of sophistication. But one thing I've been involved with most recently is a collaboration with people in the Alan Turing Institute who have been doing some work on tools for data wrangling. Again, what I'm sort of showing here will be a programming language aspect or programming language view on this problem. So this bit is going to be really about sort of if you, well, all my examples so far used relatively clean data set. And that's not how real data on the internet looks. Typically, it's very messy. And a lot of people spend a lot of time cleaning data, getting it into the right format. And this is often just a very tedious manual process. So if you sort of download multiple files, you need to merge them, fix encoding, remove outliers, do all that boring stuff. And my colleagues in the Alan Turing Institute have been working on building some machine learning tools to help with this, which we've been calling AI assistants. Those are things like sort of Python and R packages, which you can use to parse CSV files, merge data, and so on. Now, my sort of programming language perspective is that this is something that should be a lot easier to use, and the user should be able to sort of interact with those tools to get them to do the right thing. So that side is what I'm going to be talking about. And as part of that, we've been working on this project called Rattler, which is an extension for JupyterLab, where you can sort of create a new kind of notebooks that have various nice features, like you can mix different programming languages in a notebook. It will analyze dependencies between cells, but you can also embed interactive tools as different kind of cell. And AI assistant is going to be an example of this. So switch to an example here. So this is just a JupyterLab running on my machine with this Rattler extension. And if I load a very simple notebook here, so this notebook has, let's see if I can make this bigger, has a couple of cells in different programming languages like JavaScript, R, and Python, and they all define data frames 1, 2, 3. And then I've got another cell that accesses, say from JavaScript, all the 3 different cells. And you see that I evaluated just JavaScript and R code, but not the Python code. But it does understand the dependencies between the cells. So if I evaluate this one, it will sort of force the evaluation of my Python cell as well. So it's slightly different approach to notebooks, where rather than sort of just running things in the order in which you click on things, it will run things in the order that makes sense. But the interesting thing that I wanted to show you is the AI assistance feature. So I'm going to be, I'll start by loading some data tables, and I've got my data set on aviation accidents here again. And one interesting weird thing in this data set is that it contains rows for individual countries, but it also contains aggregates for the entire EU. And so if you want to do any sort of calculation with it, you have to first remove those outliers. And you could sort of spend a lot of time figuring out how to do this with code, or you can use an AI assistant. We've got an AI assistant, we've got a couple of them. There's one for outlier detection, where I just say, I want to do this on my aviation accidents. And then that runs the assistant. And if I click here, I get a list of suggestions of what you might want to do with your data, or how you might want to filter your data. And what it basically does is that it looks for every column, and in the column, it looks for the most outlier values. So basically things that are sort of the most number of standard deviations away from the mean. And it does actually helpfully finds that this geo and CRegis, the registration code and the place where this happened, the most outlier thing here is EU28, because that's the sum. So I can use this assistant to filter out all this invalid data, and then I can name my data set. And if I've got some Python code here, then I can just access this data frame that I sort of obtained through this AI assistant. So what's happening behind the scenes is that there's some sort of clever algorithm which can use more sophisticated machine learning or simple statistics like the example I had, which is sort of exposed through this simple user interface. And again, the main interaction is you select a thing from a list of options. Now, where the sort of programming language perspective here becomes useful is that you can actually come up with a sort of theory or a definition of what is an AI assistant. So for the formally minded people in the audience, an AI assistant is just something that works with expressions that represent cleaning scripts, works with some data, and it works with traces of human interactions, which is basically a sort of trace of where I clicked. And then an AI assistant just has some evaluation function that, given a cleaning script and a data, produces new data. It has an operation that, based on human interactions, that like sort of did with the assistant, recommends the best cleaning script. So if I sort of click around a bit on things I want to filter, it will give me a script that I can then apply to the data. And the most interesting thing it does is that, given past human interactions, it will give me a list of possible things I can choose. And there's an empty thing, initial value to start with. So I think what's sort of nice here is that the programming language perspective gives you a very clear, very simple take on what this thing is. And I'll show you one more example of the AI assistant idea. And this is one that actually does something pretty clever behind the scenes. So I've downloaded here data that the UK government publishes on broadband quality, and they collect a data sample in every year. I've got some data for year 2015, 2014, and they publish this online somewhere, but very conveniently every year they will rename all the columns, they will add some more columns, and they will drop some other columns. So you have very, very messy data that is just a nightmare to do anything with. And so if you want to do some sort of comparison across years, the problem is, how do I merge the data? So what I've started with, I've taken the data for 2015, and I took just upload speed, download speed. I forgot what this is. Oh, this is sort of time needed to load a page. Which part of the UK is this? Whether it's urban or rural area, and what was the latency. And now I want to use an AI assistant to basically automatically find matching columns from the other data set. So I'm going to use 2014 as my dirty data set, 2015 as my clean data set. And what I want to do is to get the matching columns from 2015 for all my columns in 2014. And if I do this, then it will try to do the matching, but by default, I think it finds the urban rural upload download latency and web download time, but then it sort of uses this distance band incorrectly sort of matches that incorrectly with one of my other columns, and I can use this plus button here to see what constraints I can sort of give the AI assistants as feedback. So it did match the distance band with urban rural and urban rural with nation. So what I can tell the AI assistant is, for example, don't do this particular match, and then I select that here, and the AI assistant will go back, do the machine learning tricks behind the scenes, and come up with a new matching, which now actually matches everything correctly. And the sort of difficult thing here was that the 2015 data set doesn't contain data on whether this is in Scotland, England, Wales, or Northern Ireland. So the AI assistant first tried to find some column which had roughly the same structure, the same number of categorical values, and that was wrong. And when I told it this was not right, it figured out that this just has to be filled with NA. So this is a sort of more interesting example where the cleaning script is a list of patches that you apply to the data, and the user interaction generates these constraints which say, don't do a particular thing, like don't match this column against that column. The data-diff AI assistant really is just these three operations. One, to apply the patch to a data set, one, to give me the best set of patches it can come up with based on the constraints I specified, and one that, given constraints I specified, offers the next set of most interesting, most reasonable constraints I might want to add. So that's the three examples I wanted to show you. And just to sort of say a few words about what this was really about. So my sort of summary highlight of the talk is that this was really one weird trick to make your data exploration simple. And the trick that was really in all these three examples was this interaction principle that I call iterative prompting. And it's basically programming by choosing from a list. And this is a thing that started with F# with type providers, which sort of operate in a richer programming language, but you do a lot of data access in this way. Really the idea is sort of how much you can do if you restrict yourself to programming mostly just by asking the environment, what are my options, and choosing one of them. And the premise is that this is much easier than sort of coming up with code by sort of opening your text editor, staring at it, and coming up with what do I want to type. In human-computer interaction, people have this sort of idea that recognition is easier than recall. So you have to sort of, choosing a thing from a list is always going to be easier than coming up with what you want to type. And I sort of looked at various aspects of this. Some of them were in a text context. Some of them were more user interface oriented. Some of them covered things like data querying and data access. Some of it covered things like data cleaning. But really, it's sort of the same trick in all three cases. And the sort of final words, really, why this is interesting. So first of all, I'm sort of coming to this domain from the programming language background. And I think programming language is sort of, people think of it as mathematics very often. I really like to think of it more as design, because it's sort of, you're designing new ways of approaching problems, and that often means changing how you think about it. So good programming language will change how you think about the world. And I think we have much more that can be done on this front. The sort of theoretical approach that, again, is sort of inspired by my past background, is to constrain yourself to simple systems or sort of simple formal world. But I think this has the sort of benefit that constraints are always good for innovation. If you sort of constrain yourself, you have to not worry about particular problems, sort of forces you to creatively think about the problems that are left. And the sort of specific interesting idea I was exploring is this thing I call iterative prompting. And the open question is, can you actually do anything in this way? And I think the answer is, the honest answer is sort of, because you have this sort of first level interaction where you can choose from a list, and that's very easy to do, but it always depends on sort of how complex is the structure of what you've got behind the list. So rather than sort of saying, this is easy, this is sort of normal way of programming is hard, my way is easy, what I'm really trying to say here is, this way you can structure the solution so that sort of easy things come first. And then if you need to do more complicated things, you can learn those as you go. So it's more about sort of factoring of complexity than about making hard things somehow magically easy. And I think that's really the sort of interesting design question there. And I did show you a lot of things. You can actually find all of those on my website, tomasp.net, which I've recently updated so that it includes links to all the work I've done in the last 10 years, which wasn't the case just a month ago. All right, that's the end. So thanks very much.